In AS-level physics, you learned the golden rule of electricity. Opposite charges attract and like charges repel. But you never explored how that force actually crosses empty space. In this unit, we introduce the electric field, an invisible region where a stationary charge experiences a force. This topic sits at the absolute core of A2 physics. It parallels everything you just learned in gravitational fields, but with a crucial twist. Electric forces can repel as well as attract. We are going to move from vectors to scalars and from the macroscopic world to the microscopic. We start by defining exactly what an electric field is and measuring its intensity. The Cambridge examiners are incredibly strict on definitions here. You must anchor everything to a unit positive charge. You will learn to map these invisible fields using field lines and calculate the exact force experienced by any particle that wanders into them. A great exam strategy. Whenever you get stuck visualizing a field, just ask yourself, what would a tiny positive test charge do right here? Next, we look at uniform fields, like the constant field created between two charged parallel metal plates. This is where your AS-level mechanics makes a massive comeback. Because the field is constant, the force on a particle is constant. That means you can use your classic kinematics equations to predict the exact parabolic path of an electron fired between the plates. It is a guaranteed A-star discriminator question in paper 4, linking electricity directly to projectile motion. Then we zoom in on isolated point charges. You will use Coulomb's law to calculate the exact electrostatic force they exert on each other across a vacuum. The electric field strength of a point charge follows an inverse square law. It is mathematically identical to Newton's law of gravitation. You just swap mass for charge and the gravitational constant for the permittivity of a vacuum. Master the inverse square law here, and you master both topics. Finally, we switch our toolkit from vectors to scalars. Working with forces and field vectors in 2 dimensions gets mathematically messy, so we introduce electric potential and electric potential energy. Because energy is a scalar, you can bypass vector triangles entirely and just add the values algebraically, as long as you keep track of the positive and negative signs of the charges. The defining visual of this unit is how these quantities change with distance. Field strength drops off steeply as an inverse square, while potential drops off more gradually. The gradient of the potential curve gives you the negative of the field strength, a relationship you will be tested on constantly. So that is the big picture. You are going to map electric fields, calculate forces using Coulomb's law, and use scalar potentials to solve complex energy problems. This unit builds the foundation for capacitance, magnetic fields, and quantum physics later in the course. Keep your vectors and scalars strictly separated in your mind. Lean heavily on your gravitational analogies, and you will do brilliantly. Let's get started.